Okay, hello guys. So this will be our second lecture on the triple integrals. So for the afterwards sections, 15.7, 15.8, and 15.9, we're going to introduce on different types of change of variable in triple and higher dimensional integrations. 15.7 will be focused on the cylindrical coordinates. 15.8 will be focused on the spherical coordinates. And 15.9 will be focused on general coordinates that you wish to pick. So all of those kind of things are techniques to integration. There will not be big theorems there to analyze. So we'll be focusing on the examples. So let us start lecture. In this section, we're learning about the cylindrical coordinates, which is actually not really different from polar coordinate. You can think of the cylindrical coordinate as polar coordinate plus the z coordinate. And it is actually defined as that format. So given a point x, y, and z belongs to the R3, a three-dimensional coordinate, we may represent it as r, theta, and z, where z is the same thing as this height z, and r theta is the polar coordinate of x and y. If you don't feel familiar with polar coordinate, you can either check up 15.4 or 15.3, the double integration application on polar coordinate, or supplement to 14.2, the limited continuity, where we introduce polar coordinate in depth in the supplement video. Okay, so yeah, that is basically how you translate the Cartesian three-dimensional coordinate into a cylindrical coordinate, which is translating the first two coordinate, x and y, towards polar coordinate. And of course, we don't really restrict you guys on the choice of x and y. If something is symmetrical in y and z, then you can choose y and z to be r cosine theta and r sine theta, where x is fixed. So this kind of coordinate system will be useful when we're considering some function or the domain of integration whenever they are symmetrical with respect to a line. Because basically this coordinate got this name because we're dealing with x and y being symmetrical, right? X, y being r cosine, r sine, whereas z can be anything. So in this case, it'll be nice if you observe some function or domain of that symmetry, then we should apply this coordinate system to change the variable and do the integration so on. Okay, so yeah, always after an introduction of integration, we should try some examples. So first of all, let us translate this 1 minus 1 in Cartesian coordinate back to cylindrical coordinates. And we translate this 2, 4 pi over 3 minus 4 to Cartesian coordinate. Okay, so yeah, basically to change into the polar coordinate in the first two variable, you can do 1 plus minus 1 squared and take a square root, right? That's the radius in terms of this figure. So be careful with this because we're gonna learn another coordinate system, which is called the spherical coordinate. In that case, the so-called radius will be the distance from this point to the origin. But the r now is simply a distance of 1 minus 1 towards the origin. Okay? So it's 1 squared plus minus 1 squared instead of 1 squared plus minus 1 squared plus 1 squared. And radius is now root 2. And theta is given by the inverse tangent of y divided by x, adding up with the correction term. So the correction term exists because we have a restriction on the range of the inverse tangent. If you recall, inverse tangent are restricted within minus pi over 2 to pi over 2. So minus 90 degrees to minus 90 degrees. And that is due to the fact that tangent has some sort of discontinuity and periodicity. So we cannot extend that domain up to the whole real numbers. And the correction term behaves in this way. So when we're dealing with a point which is in the first quadrant, you don't have to do anything. When you're dealing with a point which is in the second or third quadrant, then you have to add the inverse tangent value to pi. And when you're dealing with the fourth quadrant, which is in our case, you have to add 2 pi. So we see that this tangent inverse of minus 1 will be minus pi over 4, the minus 45 degree, which is here. And it actually corresponds to 315 degrees, right? 7 pi over 4. So we have now the radius and also the angle. So it'll be root 2, 7 pi over 4, 1. And the Cartesian coordinate is even simpler to convert to because you simply have r cosine to be the first coordinate x, r sine to be the second coordinate y, and just keep the z minus 4 here. So cosine for power of 3, which is 240 degree, is minus half. And you have minus root 3 over 2 here. So that's in the third quadrant, which you finally get minus 1, minus root 3, and minus 4. So it is actually really simple to translate between Cartesian and cylindrical, Cartesian coordinate in 3D and also cylindrical coordinates. And it is just basically polar coordinate in some sense. Yeah. Okay. So now after we learn how to translate those coordinates, let us do the formula for the integration. So let me erase this first. I actually have this written down before because I have already recorded this video, but I forgot to I mute my mic, so there's no sound. I have to do this once again. Okay, anyway, so we're integrating on this region. R theta z given by the cylindrical coordinates. R is the radius, theta is the angle, z is the height. Where the domain can be described if in the sense that theta is between some constant bound, alpha and beta. R is between some functional bound, v1 theta and v2 theta. This is called phi. And z is bounded by some function in x and y. So psi 1 xy, psi 2 xy. There is so many different ways to pronounce this. This is also a Greek letter. And I usually just do psi because that is how most math people pronounce it. But I believe there's maybe some more decent way to pronounce it. I will just mention psi in this whole section. So in this case, you have the corresponding Fubini integration theorem, which that you can translate this triple integral into layers of one-dimensional integration. So let us do it. The triple integral of some function over dv is given by, you always evaluate the constant boundary in the exterior outmost integration. And then in this case, we have v1 theta and v2 theta as the boundary for r. And then don't forget to change your variable x and y into r cosine, r sine in the height boundary. So those will be v1 r cosine theta, r sine theta, v2 r cosine, r sine. And don't forget to change your variables r cosine, r sine, and z. And dz, dr, d theta. And since we're changing into polar coordinate, right? So x and y variable gives you an extra differential term, r. So this is very important because based on my experience, there's a lot of students always forgetting that term. That term characterizes the different computation of the infinitesimal area, which is like a small parallelogram or a small rectangular region, in terms of the Cartesian coordinate and the polar coordinate. The polar coordinate will be a multiple of r if you're computing a same area using the extra coordinate. So that's why the r is here, right? Don't forget that. There's always three things when we're dealing with the change of variable. I will be emphasizing this throughout 15.7, 8, and 9. So one thing, the first thing, obviously, you have to change the integrand. That is the sole purpose of doing change of variable, right? We want to reduce the integrand. So in this case, I change it into r cosine, r sine, and z. The second thing is to change the domain or to change the boundary. So you want to change the integration domain or the boundary into something in terms of r sine, r theta, and z, or whatever coordinate you're choosing. The third thing is also important. It's the so-called Jacobian. We haven't formally defined this term yet. We'll be defining this in 15.9, but that is basically a term that is addition to the coordinate system that you're choosing. So you recall that in the usual one-dimensional integration, we know that you can always do this change of variable, right? This will be u a u b f of s ds. This is the usual change of variable formula in one-dimensional space. So this u prime t is something like the so-called Jacobian, the differential term, additional differential term, if you want to change the variable. and that is R cubed. We will again introduce a very general formula in 15.9, but for now, for the cylindrical coordinate, we have to add this extra R cubed. Okay, so three things: integrand, boundary or domain, and thirdly, the Jacobian. Okay, right. So let us start with like a bunch of examples to see how this cylindrical coordinate Fubini theorem entails anything new in our integration. So first of all, I want to integrate this function x plus y plus z over the region E, where E is a solid in the first octant. So basically, x and y and z are all positive, which lies below the paraboloid 4 minus x squared minus y squared. So an important point for you guys now is that we're introducing a bunch of different techniques in integrations, and the kind of learning object for you guys is to know when to apply what technique. And in particular, in this case, when to apply what coordinate system. In this case, you see you have a symmetry in x and y, right? They're symmetrical with respect to the z-axis, because when x is r cosine and y is r sine, then this is simply r squared, right? It does not depend on the angle. Every angle looks the same. So based on that symmetry, we should choose the cylindrical coordinate system. Okay, we will see soon, maybe later in the spherical coordinate section, I can maybe try to perform the calculation of this guy. It'll be a little bit more difficult because this thing is not symmetrical with respect to a point. So in this case, a cylindrical type of integration will be nicer. So basically, let us first write down the description of the region. In terms of x and y and z, we know that obviously x and y and z are all positive because we're working with the first octant, and that the lower bound for z is 0, the upper bound will be the paraboloid 4 minus x squared minus y squared. So in terms of r and theta, it is actually quite intuitive that based on xy being larger or equal to 0, we have that our theta is within the first quadrant, right? 0 to 90 degrees, 0 to the power of 2. And this natural restriction tells you that x squared plus y squared should be less or equal to 4, or basically x and y are contained in a disk with radius 2. So you have 0 less than equal to r less or equal to 2, whereas theta is within the first quadrant. And z, as I mentioned before, simply is bounded between 0 and 4 minus r squared. So based on that description, we can now perform our integration. So the triple integral by Fubini theorem can be written down in terms of, first of all, replace the integrand. X is r cosine, y is r sine theta, and z is just z. And for the boundary, the constant boundary theta goes from 0 to pi up to the power of 2, and r goes from 0 to 2. Whereas the last term, Jacobian, don't forget this r, there's always an extra r when you're performing the cylindrical coordinates. Okay, and maybe a remark here is worthwhile. So obviously in the previous sections, we always try to do some change of order of integration, right? Sometimes it'll be beneficial, sometimes not. And most of these cases, because the purpose of changing things in the triple integrals is to make life easier. We already tried to make the, say, the region or the function to be as simple as possible by translating them using the cylindrical coordinates. So in most cases, when you're dealing with this triple integration, most of the time the order will be angle, radius, and then the height. Obviously, in this case, maybe abstractly you can change these two variables, maybe z and r can be interchangeable, but that will not be too efficient because, as I mentioned, we already do something to make life easier. And so there's, in general, not really a point to change integration to make things even simpler. I hope that makes sense, but yeah. Basically, every integration stuff almost all depends on experience. So that's why I very encourage you guys to do as much exercise as possible so you guys can get a kind of a sense on what type of technique, what type of coordinate system you want to use during this type of problem. For now, we're dealing with each technique a section, so it'll look straightforward, but in general, it is not that straightforward. Okay, so now after translating everything using Fubini's theorem, then it's painful integration and actually quite simple. So for the first case, we're integrating with respect to z. So this whole guy is a constant. You have a extra multiplication of z here, and zr simply gives you z squared r divided by 2. Plugging in the corresponding boundary, you will get this big stuff, And the first term is harmless because this is just a polynomial, right? The second term is also really nice because you see that there's an extra r here. So we don't really have to expand this guy due to the fact that we can use something like u sub, maybe u to be 4 minus r squared. Then the differential du can be sort of canceled out with this r dr. At the end of the day, we will get the anti-differentiation to be minus 4 minus r squared cubed over 12. So yeah, then you plug in the corresponding points, you get a constant in that term, and you will get a, oh, yeah. And then you will get a constant here, where cosine gives you anti-differentiation sine, sine gives you anti-differentiation minus cosine, and this guy is just a constant, so you multiply that by daily. Plugging in the 90 and 0 degree, the constraint on the first octant, first quadrant, you have this number. So you see that everything here is not really tricky. The only thing important is here in this section. Translate something which has a function or a domain that is cylindrical, cylindrically symmetrical in some sense, then you should translate that using a cylindrical coordinate with an additional factor r. All right. Now for our second example, it is also an exercise from our textbook. And in this case, we want to find the volume of the region E described by these two surfaces. The upper boundary is the paraboloid z equals to 24 minus x squared minus y squared. The lower boundary is a cone 2 square root of x squared plus y squared. So this thing has a nice curvature like this. It is a cap, and this is a cone. So it has a pointy vertex at the origin like this. Okay, so obviously with that kind of picture in mind, you can see that first of all, it is obviously symmetrical with respect to the z-axis, right? Because x and y plays the same role here. So one should consider applying cylindrical coordinate in this case, due to the fact that you have simply r squared here. Secondly, the volume of this guy is simply a triple integral over the whole solid, right? In particular, the upper bound, in terms of the xy coordinate, it's very simple to describe because the upper bound is simply this guy, lower bound is this guy. So the whole thing to consider is simply the domain of integration of x and y, which can be computed by assuming that these two guys intersect. So the lower cone expand up to some point, right? And the upper paraboloid, the cap goes down to some point. And that cap will intersect with this cone at some height z, and that is what we're interested in, because that will be the maximized x and y region. And for that region, if we integrate on that thing, then the height and compute the height and integrate over all those regions, you'll get the volume. So basically, let us first solve the corresponding height or radius. So let us set the z to be equal. And you get by replacing x and y by r cosine r sine, that r is simply 4 or minus 6. You can do that by any way you like. You can do quadratic formula, you can do factoring the linear factors, but anyway, you get r equals to 4 or minus 6, right? So minus 6 does not make sense because radius is never negative, so we're dealing with 4. The intersection of the paraboloid and the cone is at the point where x and y are in disk of radius 4. So the solid can now be described in terms of the cylindrical coordinate in a really nice manner. R is between 0 and 4, theta is between 0 and 2 pi, it goes all the way in the z-axis, right? And z is lowerly bounded by 2r, upperly bounded by 24 minus r squared. And then it's really simple. So the volume is simply the triple integration over 1 on that solid. Whereas don't forget your r, very, very important. And then it's a simple, very simple polynomial integration, which you finally get 512 pi divided by 3 unit cubed. Okay, this is the volume of these particular objects. Right. The second question asks us to find the centroid of E, which is a terminology we haven't defined yet. So centroid of E, as they mentioned here, is a center of mass in the case where density function is a constant. So we also haven't defined a center of mass yet, so let us do it here. So basically, okay, say this is a one-dimensional object, this is open. So the center of mass will be at some point that if I put my finger here, then it should be balanced out. Okay, it's a little bit difficult, but anyway. So at some point it is balanced out. That means that the mass distribution on these two guys actually is centered at this point. And if we have an even more complicated object, okay, say this book here, then maybe the center of mass is somewhere here. Since it is a three-dimensional object, so okay, it's hard to balance, but anyway, you get the idea. So you have a variously distributed density object, and that object can be considered as centralizing those mass at some point. And that point is called the mass of center of mass. Okay, yeah. And then to evaluate that center of mass, there's a very nice kind of formula. So let us first introduce the formula, and I will go through the meaning of this thing. We integrate this is called the coordinate vector or the positional vector, x and y and z, to rho x, y, z. This is the density at the point x and y and z, infinitesimal density to be precise, over the volume dv, divided by the actual mass, which is the integration of the density function over the solid E. So don't get me wrong, this is a very simple notation. So I'm simply saying that we integrate x times rho to get the first coordinate x bar, y times rho to get the second coordinate y bar, and so on and so forth. So if you recall this type of formula from, I think, section 15.4, application of double integrals, this thing is very much like the so-called expected value, right? The average of x. And that is precisely what it is saying. That is saying that how much mass is distributed at the point x. And if we integrate all those things with respect to the position, the theoretical position, then we can figure out at which point x should we consider as the center of mass in the x direction, and so on the y direction and z direction. So this corresponding x bar, y bar, and z bar is the point where we can consider this object to be a point, to be this strange figure into a infinitesimal point. That is how sort of like physicists deal with this stuff. We have so many different types of shapes, objects, different matters, materials, but to be able to consider them as a single point, where should that point be? That point will be of this x bar and y bar and z bar, the center of mass. Okay. In this very particular case, when rho is a constant, then you see that this will be, say, 4 and 4, and these two 4 cancels out, right? So in that case, this is for a centroid, and the formula reduces into something like this. We don't have to care about density because it's a constant and it divides each other in the numerator and denominator. Okay, so if that's all, let us do the computation. We already know that the volume is given previously by 5.2 pi divided by 3. So you have that reciprocal here. And the integral here is actually exactly same as the previous case. Only the difference is that the x is arccosine here. So we don't have 1 there. And despite the computation here, I would suggest maybe if you understand the definition of the center of mass, then basically even an elementary school student should understand that this guy is very symmetrical, right? In particular, it is symmetrical in x, y respect to the z-axis. So since you have this symmetry, the centroid or the center of mass of x must be 0 because everything is uniformly distributed between the rightmost boundary of x and the leftmost boundary of x. And same thing happens for y. So both of these centroid must be 0. And that actually reflects in our computation. So see that the cosine actually integrating over theta from 0 to 2 pi is actually 0. So it reflects our intuition, making the x bar and y bar to both be 0, despite what the volume is. The only interesting thing is the z, because the z is not uniformly distributed. The upper and lower bound are of different shapes, right? The upper is a cap, the lower is a cone. So it'll be interested in computing this coordinate. And it is again a very tedious integration. For z, you don't have to change the variable because z is just the in cylindrical coordinate. So doing the integration, which I omit here, it should be a very simple one-line polynomial integration. You get 5888 over 3 pi, which is the contribution of each coordinate to the mass. And then you finally get 23/2. So at a so-called centroid, x bar, y bar, z bar, to be 0, 0, 23/2, you can consider that strange solid into that point. In a sense, if you want to compute, you want to analyze, say, the motion or how force acts on this object. Okay. As I mentioned in section 15.4, I won't be quizzing you on this kind of physics thing or probability thing. If I have to, then I will provide you the formula. So you don't really have to understand this. You don't have to understand this physically, just mathematically, I would say. Okay, our last example is on the volume of this solid, which we have introduced in section 15.5, the surface area. We have introduced various ways to compute the surface area of the solid, which is called the Steinmetz solid, right? So let us introduce this again. It is basically enclosed by two cylinder. One is x squared plus z squared equals to 1. One is y squared plus z squared equals to 1. And as Julian provided, the blue surface is the surface x squared plus z squared equals to 1, whereas the yellow surface is y squared plus z squared equals to 1. So since it is like again symmetrical, right? So we should maybe assume that we can use the cylindrical region, cylindrical coordinates. So in this case, the symmetry of the cylinder is respect to the x-axis and the y-axis. Obviously, you can maybe rotate the this solid because it will rotation preserve the volume, right? You don't have to do anything if you do the rotation. So you can maybe make life easier by considering the xy coordinate as r cosine r sine. But in this case, I just want to demonstrate that it is completely fine if you want to consider xz or yz to be of the polar coordinate and preserve the other coordinate x, y, or z. Okay, so first of all, in terms of the description in terms of x and y and z, it is simply enclosed by x squared plus z squared equals to 1 and y squared plus z squared equals to 1, right? However, it is more approachable if you describe that in terms of r, theta, and y. So r now is the radius of x and z in terms of the polar coordinate. So we see that the blue curve now becomes r squared equals to 1. And that the yellow curve is equal to y squared equal to 1 minus z squared, which is 1 minus r squared sine squared theta. So for x and z, basically this circle, you're computing everything all the way from radius 0 to radius 1 and all the way from 0 to 2 pi. So those are quite simple. And for y direction, the lower bound is given by, this should be upper bound, is given by positive square root of this guy. And lower bound is a negative square root of that guy, which is minus square root of 1 minus r squared sine squared. That's equal to y, that's equal to the corresponding positive upper bound. And now we can compute the volume. So again, the triple integration can be using Fubini theorem to evaluate. You have the angle integration, radius integration, and also in terms of y coordinate. And don't forget the r again. Very, very important. And it'll be a really nice habit for you guys to do integration because it is so tedious and complicated that try to use symmetry or any type of simplification at the first few stages because it'll make life easier a lot. In this case, we know that due to a symmetry, if you cut, say, this solid in 4 halves, then in the first quadrant, second quadrant, third, and fourth quadrant, they all share the same volume. So that is exactly what I do. I factor out a 4 and I reduce the integration into 0 to the power 2, only the first quadrant. A virtue of this is that when you're considering 0 to the power 2, you're dealing with everything inside the first quadrant, right? So the good thing about it is that you don't have to care about the signature of sine cosine. They're always non-negative. And that is very good in the sense that you don't really have to deal with absolute values when you're taking square root of something. So now we have this nice integration. Don't forget that I already integrated y, so you have double this guy, where double comes to here. And now this is a relatively simple integration. You have an r here, you have an r squared here. So the natural idea is to use up inside the square root, whereas the du has a factor that can be cancelled out with the r here. So now you have u half du divided by the corresponding differential. And the upper bound reduces to 1 minus 1 sine squared, which is cosine squared. And the lower bound reduces to 1 minus 0, so that's doing the anti-differentiation of u, square root of u, you get 2 over 3 u to the 3 over 2, right? And by plugging in the upper and lower bound, you can get 2 over 3, 1 minus cosine cubed, and this 2 is cancelled out with this 8. And you have extra cosecant data here, cosecant square data. Now, there is so many ways to perform this integration. You can do so I want to mention here that basically if you have a bunch of guys in terms of cosine and sine, a bunch of polynomials in terms of cosine and sine, it's always computable, although painful, because you can use something like the double angle formula, triple angle formula to reduce everything up to some cosine of large angle or small angle. So it is in some sense always doable. In this case, I try a tricky kind of way to do this. So let us recall that you have this nice formula. A cubed minus B cubed is always A minus B, A squared plus AB plus B squared. Applying this to A being 1 and B being cosine theta, then you should get 1 minus cosine theta, 1 plus cosine theta plus cosine squared theta. And let us apply again the square differences. A squared minus B squared is A minus B times A plus B. So you get that 1 minus cosine will be equal to 1 squared minus cosine squared divided by 1 plus cosine. In particular, by the Pythagorean theorem, 1 minus cosine squared is sine squared, right? So divided this guy and this guy, you get a really nice integrand, which is 1 plus cosine squared divided by 1 plus cosine. Now, observe that the latter term here gives you cosine. And the former term, I simply recorded here, 1 over 1 plus cosine theta. And this is actually really nice news because based on the double angle formula or half angle formula, depending on what you call it, 1 plus cosine theta is simply 2 cosine squared theta half, right? So why is this good? Because the reciprocal of that guy will give you something like secant squared, which we know that it is the differentiation of tangent, right? So the anti-differentiation of secant squared is always tangent itself, which gives us tangent theta over 2 plus sine theta. Plugging in the corresponding boundary of theta, you get 16 over 3 unit cubed. Okay, so yeah, it's a little bit painful, but yeah, I tried to introduce as much like technique in the examples that's used up. There is IBP somewhere in the previous videos, and there is some trigonometric identities. However, you can see that this will not actually be a very good idea, right? Because somehow this solid seems to be more of a rectangular solid in comparison to a cylindrical solid. So let me first perform the second method. We can actually do this using calculus 1 technique, the single integration technique. So if you guys recall, I don't know the exact section, but there is a way to compute the volume of some solid by slicing it. So if we slice a solid and each slice has a particular shape that we know how to compute the area of, then we can add up those shapes and get the extra volume of that solid. So in this case, it is tempting to cut the solid at the level of some level z, because you can see that if we slice z, say at the point A, then this thing, the yellow curve, will reduce to y equals to y minus a squared plus minus, right? That is this line and this line. And this also reduced to x equals to y minus a squared taking square root plus and minus. So it's actually a square in each slices, in each sections. Precisely if we slice the Steinmetz solid at the point z equals to a, whatever a is, then you have this sort of section when you're slicing. Given this particular a, you have y equals to plus minus square root of y minus a squared, and the same thing happens for x. Therefore, you actually have a square of side length 2 root 1 minus a squared for each a. And therefore, you know the area for each slice, right? You can now integrate that slice using one-dimensional integration. So the volume is simply the integration of the area of the square times the width of the square, thickness basically. And if you multiply them together, you get actually a polynomial integration because you don't even have a square root, right? You have z minus z cubed divided by 3, plugging 1 and minus 1, which gives you 16 over 3. So you see that this is way simpler than our method 1, and that is basically due to the fact that this is more of a rectangular region thingy in comparison to a cylindrical thing. After this kind of intersection, there is not much circular feature preserved in this particular object. So it will be easier to compute it using a simple Cartesian coordinate. However, I strongly encourage you guys when you're doing every type of integrated problem, try different coordinates as well as possible using polar coordinate in two-dimensional system, using cylindrical, spherical coordinate in 3D system. Try to use every type of thing to see what kind of domain or function is the thing that when you observe them, then you should use some particular system. Okay? Just a small remark here. So combining with our previous fact in 15.5, we now know that a Steinmetz solid, which is created by two cylinders of radius r, has surface area 8r squared and also volume 16 over 3 r cubed. Okay. There's also a small extension. Maybe I can leave it as an exercise. So this is a bi-cylinder created Steinmetz solid, right? There's also you can also create it by three different cylinders. You have this X, you have this Y, and then we intersect the Z up to this bicylinder Steinmetz solid. Now, try to describe that solid in terms of X and Y and Z, or this R, theta, and Z, and evaluate the corresponding surface area and the volume. That'll be a very good exercise. Okay, so just to recall what we have done in this lecture, basically this formula. So we now know the cylindrical coordinate is simply the polar coordinate plus the z coordinate. And whenever you have this type of symmetrical region of integration in the triple integral, then you can use this New-Fubini theorem with an extra factor of r to compute the iterative integration. Okay. Right. In that case, I will see you guys in the next video on spherical integration. So see you.